This video serves as an introduction to molecular geometry. Up until this point, we've learned how to draw molecules through Lewis dot diagrams or Lewis dot structures. So what is molecular geometry? Well, just like it sounds, it's the geometry or shape of molecules. When we were drawing Lewis dot structures, it was easy to think that molecules are just on paper or planar or two-dimensional. But in reality, molecules are actually three-dimensional and they have 3D structures. This is important because it does affect how they bond in reactions. So what we're going to do in this video is we're going to do an introduction to molecular geometry and specifically what's called electron domain geometry. Now, how do molecules even get shapes to begin with? Well, remember, molecules bond through their electrons, and electrons, all being negative, want to repel one another. When these electrons repel from one another, they create the shapes. So depending on how many electrons are in their valence shell and how many electron domains there are, will depend on the shape. This is called valence shell electron pair repulsion. Valence shell refers to the electrons that are in the valence shell of the atoms being bonded. Electron pair, because electrons typically come in pairs. And repulsion, because like I said, those molecules get their shapes from the electrons repelling from one another. As we go through this video, we're going to focus on the general formula ABX, where A is going to stand for the central atom, and B is going to stand for the terminal atoms, which are attached. To understand molecular geometry, we must first understand what an electron domain is. Remember from topic 6 that electron pairs can exist in two forms. Those electrons can be bonding pairs, which are involved between two atoms, or they can be lone pairs, which are pairs of electrons that are sitting on an atom unbonded. Now, it's important to remember as we go forward that bonding pairs can be single bonds or multiple bonds. So knowing that, an electron domain is defined as a lone pair or a bonded pair. Notice that we do not make a distinction between a lone pair or a bonded pair when we're referring to an electron domain. As we go through some examples, remember that double and triple bonds are only going to count for one electron domain. So let's see this in action. On the screen are 5 molecules, and all we're asked to do is determine how many electron domains do these molecules have. This is a very easy process, and I'll show you how to do that with the examples. When we're determining how many electron domains a molecule has, we're only looking at the central atom, and that's it. So don't worry about the terminal atoms and any lone pairs they may have. Remember, an electron domain is either a bonded pair of electrons, which could be in a single bond, double bond, or triple bond, or lone pairs. So let's look at water. Water, as you can see, has 2 lone pairs and then 2 bonded pairs. Total, water would have 4 electron domains. Specifically, 2 of those electron domains were lone pairs and 2 of those electron domains were bonded pairs. Let's look at another example. Let's look at the example immediately to the right. If we look at the molecule XeF2, only looking at the central atom, we see that it has 2 bonding pairs of electrons and then 3 lone pairs of electrons. So total, there are 5 electron domains, 2 of which were bonding and 3 were lone pairs. Notice that I didn't look at the lone pairs on fluorine because they weren't central. All right, let's go to the right. Let's take a look at PCl5. Notice we have 1, 2, 3, 4, 5 sets of bonding pairs of electrons. Phosphorus does not have any lone pairs on it, so there would be 5 electron domains with the molecule here. All right, let's look at the bottom left. We have HCN. Only looking at the central, let's figure out how many electron domains there are. As far as lone pairs, there's only 1. Now, how many bonding pairs of electrons do we have? Well, we have this one right here, but then this double bond only gets counted as 1 electron domain. Bonding pairs, electron domains for double bonds and triple bonds are only counted as 1. And therefore, HCN would have 3 electron domains. Finally, let's look at SO3. On the sulfur, we have 1 lone pair, and then we have 1, 2, 3 electron domains that are involved in bonded pairs. So total, there are 4 electron domains. Now that we understand what an electron domain is and how to count them, we can now move on to what's called electron domain geometry. This is not the same as molecular geometry, which we'll cover in another video, but electron domain geometry sets the stage. So we need to understand electron domain geometry first before we move on to molecular. So what is electron domain geometry? Well, simply put, it's the geometric shapes that's based on electron domains. Depending on how many electron domains a molecule has will depend on the shape that it creates. When we go through the electron domain geometry, there are 5 electron domain geometries that we'll see. For each one, you're going to notice it has a couple things. First of all, it's going to have a balloon picture. In the picture, the balloons where they're tied is going to represent where the central atom is, and then the balloons themselves are going to count as electron domains. Then you'll see it gives us the general form, the shape that it creates, the bond angle that it creates, assuming that there's no lone pairs, and then we'll give you an example. So the first electron domain geometry occurs when you have 2 electron domains. What that means is on the central atom, you have 2 electron domains attached to it. That gives us the general form AB2. When you have 2 electron domains, the farthest they can get away from each other is when they have a linear geometry. In other words, it's 180 degrees between one atom and the other. So in other words, it's 180 degrees between this atom and that atom. Now remember, this is provided no lone pairs. We'll get to that later on. An example of this is carbon dioxide. When we look at the Lewis dot structure of carbon dioxide, it looks something like this. Now, as we look at how many electron domains there are, we look at the central. There's 1, 2. Notice there's no lone pairs on carbon, and so 2 electron domains actually would yield a linear molecule. And so carbon dioxide actually is a linear molecule. Let's take a look at the second one. The second general form is AB3. This means that there are 3 electron domains that are attached to the central atom. The farthest they can get away from each other is 120 degrees, and this produces what's called a trigonal planar shape. Trigonal meaning 3, and planar meaning it's in the plane of the paper. So that means that it's going to be flat. I like to think of this as the Mercedes-Benz shape. If you think about a Mercedes-Benz symbol, it looks like that. And so that's going to be the shape of the molecule. An example of this is BF3. If we were to draw the Lewis dot diagram for BF3, it might look like something like this. And I'm not going to draw the lone pairs on fluorine, but there are lone pairs. Notice boron does not have any lone pairs. Boron is one of those exceptions that's happy with 6 valence electrons. And so when you look at how many electron domains are on boron, we have 1, 2, 3. So if I actually wanted to draw this correctly with the shape, it would look something like this. So we can see the molecule would actually have that trigonal planar or Mercedes-Benz looking shape, rather than this is just the Lewis dot. It doesn't actually represent what the molecule actually looks like. The bond angle between all of these external or terminal atoms of fluorine would all be 120 degrees. That's the farthest they can get away from each other. Now the remaining 3 geometries, 2 of which are on this slide and then one's on the next, this is where we start to get into some 3-dimensional shapes. The first 2 were planar, meaning you could just draw them on a piece of paper, but these 3 now get a little bit trickier. So the next one is when you have 4 electron domains. So we have the central atom in the middle, and then we've got 1, 2, 3, and 4 electron domains, giving the AB4 general structure. This is called tetrahedral, and tetrahedral is probably one of the most common shapes that there are. You'll see it a lot. Now, the bond angle is kind of funky. It's 109.5 degrees. That's kind of an odd one. It's the only decimal one that you'll see among all the 5. I call this one the ceiling fan one. So if you kind of imagine like the pole that comes down from the ceiling, and then you've got your blades that kind of go out a little bit, that's kind of the shape of the molecule that's tetrahedral. You've got the central atom that would be right here, and then your terminal atoms would just be attached to the blades and then the end of the pole up there. Now what's really hard to visualize, and hopefully we'll get to do it in class, is the bond angle between every single atom, including the one that's right here. They're all 109.5 degrees. There's no way that there's anything different. That's the farthest they can get from each other. So every single one of those 4 electron domains is going to be 109.5 degrees from each other. An example of this is CH4. Now this is methane, and this is a really important example. When you draw the Lewis dot structure, it's going to look like this. And so a lot of times students think that the shape of the molecule is just like a T or a cross, but that's actually not true. The shape of the molecule actually looks something like this. So you have carbon, and then here's the hydrogen that is like your pole going up to the ceiling. Here's blade number 1, if you will. Now notice these are solid lines that are right here and here. That represents they're in the plane of the board. How do you draw blades coming? You notice this balloon is kind of jutting out at you, and this balloon is jutting out behind you. How do you draw that on a piece of paper? So the one coming out at you, which would be represented right here, we're going to draw that with a wedge. So it's going to look something like this. And then the one going behind the plane of the board is going to go something like that. It's going to have a dashed line. So I know it looks kind of funky and a little weird. Actually, let me redraw this a little bit. Do it like this. Kind of more down. There we go. I know it looks a little funky, but hopefully you can kind of visualize that. And the key thing, once again, is that the bond angle between every single one of these hydrogens, no matter which two you're looking at, they're always going to be 109.5 degrees. That's going to be your tetrahedral shape. And like I said, that one pops up a lot. All right, let's look at the second to last one, which is the one right below. This one is going to have the general form AB5, which means you have your central atom, and then you have 1, 2, 3, 4, 5 terminal atoms attached to it. This is going to produce what's called a trigonal bipyramidal. Now, trigonal, meaning it comes from trigonal planar, and then bipyramidal. So we got a lot of stuff going on. What the heck is going on here? I like to tell students to visualize it like this. Imagine you're taking linear and trigonal planar and combining them together. So this would be the linear part going up and down. We call that the axial positions. And then notice 1, 2, 3. In the kind of like the sideways view, that's your trigonal planar. And you kind of combine them together. These three electron domains right there are what's called the equatorial position. So you have those two geometries that we first learned combined together. Now the reason why we call it, we call it trigonal because of those three, but why do we call it bipyramidal? Well, if you imagine taking, let's say we took strings from here, here, and here, and we drew them up, and we also drew them down. And you can't see the one that's behind, but it would be down their way. If you think about it, you're creating two pyramids. You're creating the one that's on the top and the one that's on the bottom. So that's why it's called bipyramidal. Once again, it's a really funky shape to visualize maybe on the screen, but in lecture we might be able, or especially in lab, we'll be able to see. Now, the bond angle here is actually 2 because, remember, we're combining trigonal planar, which remember was 120 degrees, and we're combining linear. Now, remember, linear was 180 degrees, so why would we say now it's 90? Well, the reason why linear was 180 was because the nearest atom from this part right here was this one, and so it was a full 180 degrees from here to here. It's not the case in this example. In this example, the nearest atom to the axial position would be right here, and so that one's 90 degrees. And so there's two angles, and you have to make sure you state both of them because it's 90 degrees between the axial and equatorial position, and then all the atoms that are in the equatorial position would be your 120 degrees. So an example of this is PCl5. We've actually drawn this one in lecture, and it looked like this. Without the lone pairs. Kind of looks like a star, but in all reality, that is actually not what it looks like. So what does the molecule look like? Well, you have the phosphorus. You're going to have 2 of the chlorines in the axial position. Notice I draw them in the plane of the screen. Then you've got in the equatorial position, one of those chlorines, which there's 3 in the equatorial position. One of those chlorines is going to be in the plane. One of those chlorines, which is represented right here, is going to come out of the board. So I'm going to do my wedge. And then the other one, which is all the way back there, that's going to be my dash. So you'll notice here is my 2 chlorines that are in the axial position. And then 1, 2, 3 chlorines are in the equatorial position. Finally, our last electron domain is the AB6, which means you have 6 terminal atoms attached. This is known as octahedral. If you look at the octahedral shape, you've got the 2 electron domains that are in the axial position. And now you actually have 4 electron domains in the equatorial position. What this creates is a really nice bond angle. It's actually 90 degrees between all atoms, regardless of whether it's in the axial or equatorial position. So it would be 90 degrees here, 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 and so on. It's 90 degrees between everything. An example of this is SF6. The Lewis dot structure for SF6 would look something like this. No lone pairs on sulfur. We'll get to lone pairs in the next video. but you're going to have 6 electron domains. You've got 6 fluorines. But that's not what it really looks like in shape-wise. So what is that going to look like? Well, you're going to have your sulfur. Here's your 2 fluorines that are in the axial position. And then we need to show 2 fluorines that are coming out of the board and 2 fluorines that are behind the board. So we do it like this, just like we've been doing. To show out of the board, we do wedges. And then to do behind the board, we do dashes. So those are the 5 electron domains based on how many electron domains there are. Now I can't stress enough again that an electron domain, it could be a lone pair or it could be a bonded atom. And we'll get to that in the next video. It's just strictly based on electron domains and that's it. So this is kind of a review of what we've gone through. This is the 5 electron domains. It shows you not only the bond angles, but it also shows you how you would draw these structures on a piece of paper.